Good day. Welcome to a very important show on the effects of acid rain on Atlantic salmon. I'm your host for today, Shalom Mandeville. I'm very proud to present to you an international expert in Atlantic salmon, Dr. Gordon Ogden III, who has been on this show many times, whom I know very well, is a very respected limnologist in Nova Scotia, has called Dr. Walton Watt as the expert in salmon habitat. Dr. Walton Watt is also a limnologist, that means specialist in freshwater quality. He's the director of the freshwater division with respect to research aspects, which is a part of the freshwater and anadromous division of the biological sciences division of federal fisheries. I guess I've been using a lot of complicated things there. So the rest of the show will be in form of a seminar so that I don't take away from the seriousness of the show. So, Dr. Watt.
Thank you very much, Shalom, and good evening, ladies and gentlemen. What I'm planning to give you this evening is a rather compressed edition of what Atlantic salmon problems have been here in Nova Scotia and how this has impacted on our rather important Atlantic salmon resource. If you would go to the first slide for me, please. There we are. This is a map. The colors show the acid content of rainfall in North America in 1980. And the little tongue that sticks out on the right is the rainfall for Nova Scotia. The bright reddish color associated with it indicates that the pH of that rainfall is less than 4.5. The normal expectation for clean rain falling through clean air is a pH of 5.6. Acid is measured on a pH scale, usually, which is sort of an inverse relationship to what the actual acid is. The higher the pH, the lower the acid content. And it's a logarithmic scale. So the difference between pH 5.6 and pH 4.6 is tenfold. The next slide will give you a indication of the distribution in terms of the acid content of the rainfall in Nova Scotia compared to what it should be. It's between 10 and 15 times normal. Now, the question facing us when we discovered this was in 1980, was how is this impacting fresh water, surface waters in the province, and how is it impacting the fish? First, let's look at the surface waters in the province. The rainfall is not uniform in pH throughout the year. As you can see from this curve, it's highest in the cold months, in the winter months, where you see snow and rain there. The pH level is higher, indicating lower acid content. And in the summertime, where the pH is very low, this indicates a very high acid content. So there's not as much acid in the rain and in the wintertime, and there's very little acid in the snow. This is because of a change in our weather patterns that occurs seasonally in Nova Scotia. Now, this slide looks quite complicated, but what it is really it's just a compass rose. North is at the top. And the colors indicate the pH of the rainfall coming from those compass directions. The black in the southwest is the lowest pH rainfall. This is less than 4.3, and that comes from the southwesterly direction. The prevailing wind in the summertime in Nova Scotia is southwesterly. And this accounts for the very low pHs of summer rainfall. The prevailing wind in the wintertime in Nova Scotia tends to be northerly. And the northerly pHs are yellow, which is less than 4.7, and the blue, which is less than 5.1. These are relatively benign pHs. So you get much higher pHs coming from a northerly direction. Now, the reason for this difference in rainfall pHs is because there's a lot of industry concentrated southwest of us, in midwestern U.S., and there is very little north and east of us because there's just the northern Canada and the North Atlantic. There's a very clean direction. Now, especially the northeast direction happens to be clean because that's where most of our snow comes from, and snow doesn't bear very much acid in it at all. You'll see this later in the impact on rivers and lakes, in that the melting of the snow in Nova Scotia doesn't actually result in an acid shock the way it does in some other parts of the world. The first data set I had access to for looking at what is the impact on surface waters was a set of lakes in Halifax County which were analyzed quite thoroughly in 1955. And we repeated that analysis in 1977. And the results are that most of our analysis in 1977 falls on the solid line here, which is a unit below the dotted line. The dotted line represents the pH in 1955. The solid line represents the pHs that we found in 1977. Every one of them had fallen in pH. But there was a problem with that data in that we had a lot of variation that could not be explained either by its geological component or any other component that we could think of. The distribution of the pH in those lakes was rather strange, but we found that we could account for it by this relationship here, which is an expression of the amount of sulfate, the amount of sulfuric acid in the lakes, expressed as a function of its distance from the Halifax power plant at Tufts Cove. So it would appear that with these Halifax County lakes, what we had demonstrated was that we had our own little acid island here in Halifax that was created not just by Tufts Cove, but by all of the industrial activity in the Halifax area. And it wasn't a clear demonstration of long-range transport of acid precipitation. We had to look further afield into a slightly cleaner portion of Nova Scotia for that. So what we did is we looked at another data set of rivers. This is not a very good slide. I apologize for that. This shows the, oh, that's an improvement, thank you. This shows the pHs of 5 rivers from, and these are monthly data collected for a complete year in 1954-55 as compared to 1979-80. And every one of those indicates a drop in pH. But again, this is just 2 points in time. We're looking at 1954 and comparing it to 1979. And you can't really say that this is the trend. It's not a straight line time because you've only got 2 points. It's important to try and establish something in between. Unfortunately, we found a data set, which is the Medway River, that would give us something in between. And the data points on here show the pHs on the average of every second year on the Medway River for the sets of data that we have. There is the straight line indicates the downward trend if we assume it is a straight line. But it's also quite legitimate. You could interpret this as showing a decline till about 1975, and then after that things seem to level off. They look as though they're going up a bit, but then the very last point on the curve is down low again, so it looks as though it might have leveled off a bit. But it tends to be a little noisy, but the overall trend since 1955 has been a decline. Now, as with the pH of the rainfall, the seasonal variation of the pH, the acid content of a river, tends to vary with the season of the year. In Nova Scotia, the pH is at a minimum in the middle of the winter. Here we are January and February, very low pH. This is an average of 10 years of monthly data from Tuscot River in southwestern Nova Scotia. When the snow starts to melt in February and March, the pH starts up. The initial flush of water from melting snow would tend to dilute any acid that's in the system. And the pH begins to rise. And then in the spring, as biological activity sets in, it starts to go up even faster. Now, the way we interpret this curve is that biological activity during the summer months is producing an acid neutralization effect. And the acid is being stored in biological tissues, in bogs, in trees, in the forests. And it stays that way until the biological activity stops in the fall. And when it stops in the fall, and there is a dieback of leaves, mostly of plants, and the rain starts in the fall, heavy fall rains, then this accumulation of acid in the biosystem is suddenly washed into the river. And that accounts for that dramatic drop in pH that you see there in the late fall. It goes down to its winter low and it stays there until snowmelt comes next spring. Now the solid curve that sort of starts on the top is the flow rate in the river. It's labeled flow. Can you focus in on that label on the left-hand side where it's flow? And the bottom curve there is the pH starting to rise in the wintertime and the flow is high. And then as the flow gets low in the summertime, the pH is very high. And then you see when the flow rises again in the fall, the pH suddenly drops. There is a very close relationship between flow and pH. And it's possible to model the pH of the river entirely in terms of just the amount of water flowing in it. This is a relationship just between the hydrogen ion, which is the acid ion, and discharge in the river. And as you can see, it's a very good, apparently straight line relationship. It's rather unsatisfactory, though, because all it really tells you is that the more water you have, the more acid you have. This is sort of a physical relationship with the river. We've been looking for try to establish an insights into what are the chemical relationships, what induces the acid. One of the best relationships is this one. It's the relationship between acid, which is hydrogen ion, which is red, and aluminum ion, which is blue. There is a very close parallel here between aluminum and acid. The cause and effect is fairly straightforward. The more acid you have in the river, the more aluminum is mobilized. And so they do tend to parallel one another very closely. Of more significance from a theoretical point of view is this relationship here. Again, the red is acid, the same curve, and the green is the sulfate ion, which would be the major component of sulfuric acid. Now we see a very good relationship on the left. About the middle of the curve, there's a sudden drop in acid. At the same time, the sulfate ion has a peak. And that's very strange. That's worth looking at. And also, a similar phenomenon occurs on the far left there, where the two diverge quite a bit. And the relationship there appears to have to do with the dissolved organic matter in the river. Now, here we see, again, the red curve is acid, and the green curve this time is dissolved organic. The dissolved organic material is actually a weak acid. But weak acids, in the presence of a strong acid like sulfuric acid, tend to act like buffers. They tend to counteract the strong acid. And so you see here where the drop in hydrogen ion has occurred. It was associated with an increase in sulfate, but it's also here associated with an increase in organic acids, which tend to be buffering that sulfuric acid. And over on the left, where this big drop in hydrogen ion, or the minimum in hydrogen ion occurs, it's associated with a peak in the weak organic acids. So even though the sulfuric was high at that time, it was being neutralized by the large peak of organic acids that occurred quite early in the fall of the year at that time. The two tend to counter one another, but putting them together, you can create a model of the acid situation in the river. And here we have, again, the red curve is the acid, and the dotted line is the calculated acid as a result of the model of its relationship to other ions in the water. The fit is quite good. Here it is again showing in terms of a straight line relationship. Fairly satisfactory, and it ties in with what we think we understand as to the nature of the dynamics of the acid in the river. Now, there's more than just the dynamics of acid in one particular river. We have to look at it from the point of view of the region as a whole. When we started looking for surface water problems related to acid rain phenomenon in the Maritimes, this is in 1979, 1980, we looked at every river in the entire maritime provinces in terms of its chemistry, looking for signs of acidification. The only signs of acidification we found, though, were along the Atlantic coast of Nova Scotia. And that is because it has a rather sensitive geology in that region. If you just go to the slide here, the geology of southern Nova Scotia, here shown in pink and orange, is very hard. The pink is granite, and the metamorphic rocks are orange, hard metamorphic rock. The soils are very thin, and these very thin soils do not produce much in the way of acid neutralization capacity. The soils north of that, those blue soils to the north of it, have a lot of acid neutralization capacity, but very few rivers make it that far. The little breaks in the that you can see, the white areas, which are relatively high in pH. The colored areas are all low in pH. The white areas are above pH 5.4. Now, the first white area on the left is the zone of the LaHave River. The LaHave River has a series of drumlins in its water base, in its catchment basin. Those are the little brownish spots shown on the map here, and it's just peppered with them. And these drumlins are actually foreign soil that was brought in and dropped by the ice, by the glaciers, and they were left there 10,000 years ago. And they do contain soil, a lot of it from the Annapolis Valley. And if you drive through the valley of the LaHave, you see what it strikes us as normal, I suppose, but to many people it would seem very strange. Normally, when you go into a river valley, you expect to see the rich farmland is in the lower part of the valley. It's on the flat bottom floor of the valley, and the hills around the valley are usually wooded. But when you go through the valley of the LaHave, the valley floor is all trees, and every hill has got farms on top of it, because that's where the good soil is. It's sort of an inverse situation of what you would normally expect. And the soil in those drumlins is maintaining the pH of the LaHave River. Further to the left, we have the Musquodoboit River, and then further to the left of that again, the next white spot is the St. Mary's River. And both of those, if you could just focus on the left of the map here, the blue area, both of those rivers go right through the orange and pink rocks and have their headwaters in that blue area, which is limestones and soft sandstones that can produce a lot of acid neutralization capacity. And that is what's protecting those rivers. Now, people are concerned about Atlantic salmon because they're socially important fish, and they're an economically important fish too. Economists tell me that an Atlantic salmon angled is worth about $300 to the local economy because of various spin-offs that occur. The salmon spends 2 years of its life in fresh water in Nova Scotia. The adults come up the river in the summer, they spawn in the fall, the eggs are in the winter, are in the river over the winter. They hatch out in approximately March. The yolk sac is absorbed by about June, and that is a very critical time. They have to start feeding. The mechanism of death by acidification is that they lose the salts in their blood. The blood becomes so isotonic that they cannot maintain life, and so they die. Unless they start feeding here, they're going to die. And at low pHs, very few of them are going to survive. At pH 5, approximately half of them will survive. At just a little bit below that, at pH 4.8, none will survive. And a little bit above that, at 5.2, just about every one will survive. Now, on the Atlantic coast of Nova Scotia, we have about 60 rivers that are known to have to be producing Atlantic salmon now, or we have documented proof that they have produced Atlantic salmon in the past. For 22 of those rivers, we have angling records that go back to 1936. And these 22 rivers are undisturbed rivers. There are a number of records for other rivers, but they have had dams built or other major alterations taking place in their watershed. If you take those 22 rivers and look just at the rivers that are of pH higher than 5, you find for the angling record that there is no trend at all. They're still producing the same number of fish today as they were in the 1930s. If you add them all together, this is what you get. A lot of noise, a lot of variation from year to year, but no trend whatsoever in the angling catch from those rivers. As soon as you look at rivers that are of pH lower than 5, you see a dramatically different picture. Everything has dropped. And some of them, the runs are now extinct. There's nothing left. In others, there's just a tiny number of fish left, usually in just one tributary. If you add them all together, the curve looks like this, a drop off to an average of about 10% of the production that could be derived from that river during the 1930s and 40s. And if you put both of these totals together, looking at this is looking just at the rivers below 5. What I've done here is I've split it at 4.7. So the red is very low pH rivers, and the yellow is slightly higher, between 4.7 and 5. The red rivers decline and the runs become extinct about 1970. The yellow rivers, there are still some left. Now, in terms of the Nova Scotia salmon production, there are 13 rivers in the red category where the run is extinct. And there are 18 rivers in the yellow category where the run has very little left, but there's probably something there somewhere, if you can find it. And if you put both of those curves together, you get this rather dramatic picture of the impact of acidification on the Atlantic salmon as a species. The upper curve in blue represents those rivers that had chemistry that could resist acidification, and the red curve is those rivers that had chemistry that could not resist acidification. I think we'll just stop it there.
Well, could you tell me, I guess you have those red curves and yellow curves.
Yes.
What about green? I mean, that means good rivers.
Yes. Most of the other rivers, all right, which would be about 33 of them, are in relatively good shape. The next category of about 15 rivers is marginally impacted. The main river is still intact, but one or two rivers, as for instance in the Lahave, have been acidified. And those tributaries that are acidified are not producing very much at all. But this hasn't had any major impact on total production of the system. And then above that, there is no acid impact. There may be other impacts, but it's not an acid impact.
So which would you consider as the best rivers for Atlantic salmon?
You want me to tell you where to go fishing, Sean?
No. I'm sure St. Mary's is one of the best.
Certainly it is, yes. St. Mary's is one of the best. And
Margrave.
Well, yes, Marguerite, certainly it is certainly a lovely river to fish on, and I believe the salmon have been restored there to a large extent. Mm-hmm. The Le Have is also a very good river, and it is being maintained by stocking. Many of the rivers that have been impacted by acidification along the Atlantic coast of Nova Scotia are being maintained by stocking. This is the most common mitigation measure that's being employed in them.
Would the stocking help for them to go through the life cycle and spawn and grow?
No. What the stocking is doing is some of the tributaries are acidic, and this lowers the overall production of smolts that come out of that river. The smolt is the form of the salmon that goes to sea, and eventually some of them will come back as adult salmon. If part of the river has been acidified, then smolt production is reduced. Mm-hmm. And the federal hatchery system, where we have capacity in our hatcheries, we're using that capacity to rear smolts, and we stock them into these acid rivers, try to bring, to counteract a little of the production loss from the acidification. It doesn't counter it all by any means, but it does help to keep
So would these
up.
smolts, when they, once they go to the ocean and come back, would they spawn?
Oh yes, these are what we do if we want to stock smolts in an acidified river is we go to the river and we collect wild stock for brood stock. Okay, so we collect the eggs from wild fish. They are reared to produce smolts, and those are released in the river, and they would come back. Okay, and then we go each year and collect wild fish. There's no mixing of strains between rivers. We try to stick with just the river, because we're very concerned that with the loss of from the of rivers, that we're losing valuable genetic resources that cannot be restored. Mm-hmm. Each river has its own genetically unique strain of Atlantic salmon.
My friends call the Atlantic salmon the Empress of the North. Would you agree with that?
It certainly would be the king of angling fish.
I see.
You don't forget it once you've landed an Atlantic salmon. Mm-hmm. I'll take the memory of my first Atlantic salmon to the grave.
I guess I got the sign to wrap it up. You have just been watching and listening to the foremost expert in the world on Atlantic salmon, Dr. Walton Watt, who is the director of freshwater division of the freshwater and anadromous section of Department of Fisheries and Oceans, and it's been a great honor to have for you being our guest. And please tune in next week to the continuation of this show with respect to liming of the Nova Scotia rivers.